Hello, calculus fans. Let's suppose we have a lamina in the shape of a half disk, and it's going to have mass density that's proportional to the distance from the center of the circle. Let's find the center of mass of the lamina. Let's say that the upper boundary of the lamina is going to be the upper half of the circle, x squared plus y squared equals a squared. The distance from a point xy to the center of the circle, which we'll place at the origin, is square root of x squared plus y squared. So we'll say that our density function is rho of xy equals k times the square root of x squared plus y squared. K is just some unknown constant. It's the proportionality constant. Remember that we said that the density is proportional to the distance from the center of the circle. So that's why we need to have a proportionality constant in there. Here's a picture. That's a picture of the lamina. It's the upper half disk. I've marked where the center of mass is going to be, but we have to carry through the calculation now. Notice that both the density function and the shape of the lamina are suggestive of integrating in polar coordinates. So square root of x squared plus y squared is r, and then the description of d in polar coordinates is r goes between 0 and a, theta goes between 0 and pi. 0 and pi because it's a half disk. So the mass is the double integral of the mass density function over the region D. So that's a double integral over D of k times the square root of x squared plus y squared. So we get the iterated integral 0 to pi, 0 to a, kr times r dr d theta. Don't forget the r. This one we can split up k times the integral from 0 to pi of d theta times the integral from 0 to a of r squared. All right, I'll spare you the details of the calculations. Pretty straightforward. We'll end up with 1/3 k pi a cubed. Now that we have the mass, we'll compute x bar and y bar. Notice that both the lamina and the density function are symmetric with respect to the y-axis. So the center of mass must lie on the y-axis. That is to say, x bar must be 0. That's great. That saves us a calculation. Now let's compute the y-coordinate of the center of mass. According to the formula, y bar is 1 over m times the double integral of y times rho. All right, the limits of integration are the same. Out in front, we've got 3 over k pi a squared. That's just for 1 over the mass. Then the thing we're integrating, notice that y, which is here, turns into r sine theta. And then we've already seen how rho is just kr. And of course, as always, for the integral in polar coordinates, we have the r, the scale change factor. At this point, there's some simplification that can be done. For example, we could cancel the k's. And then aside from that, things can be moved around and cleaned up. So we'll end up with 3 over pi a cubed, integral from 0 to pi of sine theta d theta, times the integral from 0 to a of r cubed dr. This is all a pretty straightforward calculation, and we end up with 3a over 2 pi. That means the center of mass is located at 0, 3a over 2 pi. Okay, that's all for now.